Hello and welcome. We are Team 7. Our project is the wearable device to improve vaccine efficacy. Members include myself, Michael, Ethan, Hazim, and Anjani Kumar. Our project is to create a wearable bandage that utilizes electroporation to improve the cellular absorption of vaccines. Our overall functions include a 9-volt battery source that is input into a boost converter to output a range of 300 volts. There will be 8 20-millisecond pulses applied through the electrodes. We will measure the DC resistance across the skin after each iteration of voltage until an eventual pass-fail result. LEDs are also used for operational status and battery level. Now here's Ethan with the analog circuitry.
Thank you, Morgan. The purpose of the analog circuitry is to generate and deliver the electric pulses and DC resistance test signal to the skin. It is comprised of the following subsystems: boost converter, pulsed electric field circuit, and DC resistance Zener test circuit, all of which interface directly with the device controller. The boost converter converts the 24-volt DC battery input to the desired pulse voltage, up to 300 volts DC. The logic controller determines Vout by adjusting the input duty cycle to the boost converter MOSFET gate. The pulsed electric field circuit is comprised of a solid-state relay and fine needle electrodes. The solid-state relay provides 20-millisecond pulses with voltage amplitudes equal to the boost converter output. Pulses are delivered to the skin through fine needle electrodes spaced to generate an electric field within the tissue. The DC resistance test circuit uses a Zener diode to regulate the approximate 1.3 volt DC test voltage. This voltage is applied to the skin through the electrodes and a sense resistor which provides voltage drop signals to the logic controller for comparison testing. To further illustrate operation of the analog circuitry, a virtual model was developed using MATLAB and Simulink. Certain parameters can be adjusted prior to running the simulation, such as passing voltage level, boost converter input voltage, and electrode spacing. For this simulation, the passing voltage was set to 300 volts DC, the maximum permissible by the circuit. The plots to the left show how the duty cycle and corresponding boost converter output increase after each set of 8 pulses and DC resistance testing. Additionally, the next set of plots show the individual pulses applied to the skin through the electrodes, the electrode voltage, and the resulting electric field intensity generated within the skin. The target range for the electric field intensity for successful electroporation is approximately 400 to 1200 volts per centimeter. Next is Azim, who will be discussing the boost converter design and lab test setup.
Thank you, Ethan. And now I'll be presenting the boost converter design. The boost converter is designed to step up the input voltage from 24 volts to 300 volts output. For such an operation, convenient switching frequency of 100 kHz is used and a 92% duty ratio. The configuration is the standard one with one MOSFET transistor and a diode. The 300 volts output will be fed into the middle electrodes to produce the desired electric field, which is from 400 to 1200 volts per centimeter for electroporation. For the lab test setup, the team used various lab instruments such as variable DC power supply, signal generator, pulse width modulation controller, oscilloscope, programmable logic controller, and needle electrodes. The team started building the boost converter by soldering the components into a prototyping board, as the rated current is too high for a breadboard. The team then built the Zener test circuit, which regulates the voltage to 1 volt, and that voltage is going to be used as a test voltage to measure the DC resistance drop across a test medium, such as skin. The final step was to integrate the two circuits using the PLC, which has a solid-state relay that controls the operating circuit and acts as a switch between the boost converter and the Zener test circuit. The team is then able to use the PLC program to produce the 8 electric field pulses that will achieve electroporation. And next, Anjani Kumar with troubleshooting and results.
Thank you, Hazim. When constructing the boost converter, the team encountered three main issues: discontinuity points due to the parts being incompatible with the PCB, insufficient gate driver signal from the pulse width modulator controller, and excessive heat from the MOSFET while the circuit was running. We managed to solve and overcome these obstacles by using excessive solder to help lock in the components into the board, using a proper signal generator to drive the gate, and using a heatsink along with thermal paste to help reduce the heat generated from the MOSFET. Our lab test results are 300 volts V out with 24 volts V in at a 20% duty cycle, 1.3 volts V out at the output of the Zener test circuit, reasonable heat from the MOSFET, and the PLC switches between the operating circuits. Next, back to Morgan for the FPGA.
Thanks, Anjani Kumar. We decided to take the logic a little farther and program what it would be like on a field programmable gate array. Here's the resulting flow summary using around 193 logic elements, 133 registers, and 59 total pins. Next is the register transfer level netlist. This is the overall block-like diagram of the system programmed on the FPGA. Next, we will watch a small demonstration of the logic on the FPGA. This is the example video for the PLC logic implemented on an FPGA board. So, LED 0 is our dead battery LED 1 signifies a fail, and LED 2 signifies pass. LEDs 3 through 7 are only for my debugging purposes. LED 8 is also our reset. So, right now our reset switch is on. That is switch 9. Switch 8 is our battery level. On means good, and off simulates a lower battery voltage. So what we're going to do is we're going to reset and save the state, and then start. And you see the LED 2 comes on. That means our system is fine and it is passing. It will eventually turn off. And what we're going to do is we're going to put in the reset state. We're going to simulate high voltage for high resistance. We're going to reset and start. And when that happens, we see that our system has failed, as LED 1 is now blinking. Now what we're also going to do is simulate a low battery voltage, which means that our battery is dying. We're going to flip it here to simulate that our battery is dying, and we'll see that LED 0 does come on and start flashing. This is just a small snippet of how the logic will be implemented. Now here's Michael with the PLC logic and prototype.
For the controller, we are using a PLC, an analog output card, and an analog input card. Also, in the IDE for the PLC, we have ran many simulations to test the algorithm. In this snippet, you will see the start sequence and some of the auto step logic. Though, of course, once the controller was shipped to the lab, we have had to make some modifications for integration. Looking ahead, in this case, one of the first steps of manufacturability is taking the large prototype and shrinking it into an application-specific PCB. This could end up with certain items like the boost converter needing to be a separate module, but a single PCB would be optimal. Here we have the concept PCB with a simple start button, a reset button to abort the current cycle, an application-specific IC, and the required supporting modules. Next step in these early stages is concept of design. Here we went with an IC cover, a PCB base, a battery pack, and an elastic sleeve. This initial design is optimized to be a portable standalone device with the ability to fit a wide range of end users.